All right, so we're going to look at some more stuff about linear functions. Um, Actually, let's use that guy. Some of this is review to start with. So what we want to recall is that if the points on a graph lie in a straight line, so graphically, if the points are in a straight line, then we call that function linear. So if they're in a straight line, they line up perfectly, we have a linear graph. That's how we tell on a graph. In a table, to see if a function is linear, so in a table, we have to compare how the y values change with how the x values change, both of those things. On our practice, I think some of us, we were just looking at how does the y value change, looking if that's constant or not. It's not just the y value change. It's comparing the y value change to the x value change. And the way we compare those is we make a fraction, and we call that fraction rate of change. So make sure you know that rate of change means the fraction of the changes. So it's the fraction, that's the change in y divided by the change in x. Remember, we learned this notation, delta y over delta x. On a graph, we're going to start talking about it as rise over run sometimes as well. Okay, but the key here is that rate of change is not just the change in one column, the y column, or the change in the x column. It's the comparison of both. And the best way to compare is to make a fraction. So if a function is linear, then the rate of change between all the points will always be the same, no matter which points you choose. Now remember, we're talking about the rate of change being the same. The rate of change, which means the fraction that we make of changes, right? Change in y over change in x. It might not look the same at first, but as the other rates, but if I reduce it, it will always come out to be the same number every time. So what we want to do here is we're going to look at what it means to have a positive or negative rate of change. So on a graph, they want me to sketch an increasing graph. I'm going to say this guy right here. That's an increasing graph. That line has a positive rate of change. Why is that? Because as the independent variable, remember x is our independent variable. As that increases, so in that case, it's moving to the right? If we go from like this point to say this point, as we move to the right, it's increasing. The y, the dependent variable, which is always the y, in this case, is going up. So when we say the independent variable is going right, that's the change in x is going in a positive direction. And then here our change in y is going in a positive direction because it's going up. Up is a positive direction for change in y. So when we make our rate of change, delta y over delta x, change in y over change in x, we've got a positive divided by a positive is a positive number. So our rate of change is positive. And you can tell by looking at the graph, because as you go from left to right, it's going up. That's kind of the way to think about it. Now they want us to sketch a decreasing line. So there it is. So now if I took 2 points on the graph, my delta y is now negative, and my delta x is still increasing. It's still going to the right, positive. So I'm going to have a negative divided by a positive, right? My delta y over delta x is negative over positive. I get a negative rate of change. The way you can tell from the graph is that as you move from left to right, the graph is going down. Or you can say, notice that as the independent variable, remember that's the x, as that goes up, the dependent variable y is going down. That would be a decreasing function. Again, the easiest way to think about it from the graph is an increasing function goes up from left to right. It has a positive rate of change. That means its slope is positive. And a decreasing function goes down from left to right, meaning it has a negative slope or a negative rate of change. The point where the line crosses the y-axis is called the y-intercept. So if I look on this one, that's our y-intercept. It will always have an x value of 0. So we'll say that, I don't know where the y is, but it's got an x coordinate of 0. Remember, 0 is always our x, or our independent variable. Usually, it would be something about time, minutes, seconds. So if time is 0, that means nothing has started yet. This is like the starting point because time has not started. So I'm going to say usually time x would equal 0. It usually represents time. So if there's no time has passed, if time is 0, that means we haven't started this thing yet, whatever it is. We haven't started the clock on it. So that's why we call this y-intercept the starting point. Notice it always, always, always has an x value of 0. Similarly, the x-intercept is the point where the line crosses the x-axis. That always has a y coordinate of 0. I'm going to call this x because I don't know what it is on that. It's like we don't have numbers on here, so I'll just call it x. So notice that the x-intercept always has a y value of 0. Right? For all x-intercepts, the y here is always 0. All right, now we're going to look at what happens when we have a table here. So use the data in the table below to answer the following questions. Does this data represent a linear function? So first, let's check if it's a function, because if it's not a function, we can just stop there, and it's easy to check. I check all the x's. Remember, my definition of function is every input has exactly one output. So when it's a table, we're going to see if the inputs repeat. Do any of these inputs repeat? No, they don't. So it is a function. So I'm going to say no. Therefore, these 3 dots mean therefore in math. It is a function. Now let's see if it's linear. How do you check if it's linear? You check your change in y. It goes up 1, each step, up 1, up 1, up 2. That's okay that it changed like that as long as we keep the same fraction every time. My change in x's go up 2, up 2, up 2, up 2, up 4. This looks like it's going to be okay. It looks like what's happening here is we skipped a step. That's why the x's went up doubly and the y's also went up doubly. So it says, does it represent a linear function? It looks like it does because it looks like the rate of change is the same every time. So I'm going to check. I'm going to say the rate of change on each step. I'm going to write them down. Remember, rate of change means the fraction. So 1 over 2, that's my change in y over x, my change in y over change in x, change in y over change in x, change in y over change in x, and then we've got a 2 over 4. So if I reduce this, it equals 1/2. So it looks like they're the same every time, the rate of change. So yes, this is a linear. It's linear because that rate of change is constant. And it's a function because of what we said before. No x repeats. So yes, this is a linear function, and the constant rate of change is 1/2. Does it represent an increasing or decreasing function? This is an increasing function because the rate of change is positive. My slope, or my rate of change here, 1/2, is positive. That means as x increases, y increases. Let's plot the ordered pairs from the table on the graph at once. -2, -4, 0, -3, 2, -2, 4, -1, 6, 0, and 10, 2. And then if I draw and connect those dots, I get a straight line. That makes sense because we did say it's linear. Identify the y-intercept on the graph. Name the point. Well, the y-intercept is the spot where it crosses the y-axis, and that occurs here at 0, -3. So we're going to say the y-intercept is 0, -3. Identify the x-intercept on the graph. That's up here. It looks like it's 6, 0. So we're going to say the x-intercept is 6, 0. Circle the y-intercept and the x-intercept in the table. 0, -3. I found that easily because I'm looking for an x where the x is 0, and that's my y-intercept. 0, -3 is my y-intercept. Then I look for where the y is 0, that's 6, 0. That's going to be my x-intercept. That's my x-intercept. Okay, so we're going to look at some more stuff with linear functions in class when I see you again.